Let's get right into Episode 3.1, Grid Planning and Security Standards, Planning for One Failure. Welcome back to The Explainer. Today, we're exploring the invisible rules that literally keep Singapore illuminated. We all rely on a power grid that seems, well, practically flawless. But this reliability? It doesn't just happen by accident. It's meticulously engineered through incredibly strict planning and security standards.
Think about this for a second. Somewhere on Singapore's grid, right now, a transformer could fail without a single second of warning. Or, a generator could just trip. A transmission line might get compromised, but it doesn't take down the island. You wouldn't even see a flicker. So we have to ask, why?
Well, the answer lies in one foundational rule. The entire extra high voltage, or EHT, and high voltage network is built to withstand the sudden loss of any one single element. The grid is essentially built on the assumption that something will eventually break. Because let's face it, in any complex system, something always does, right? The strict rule here is simply that this one break can never, ever leave anyone in the dark.
In engineering terms, we call this the single contingency criterion, but you'll usually hear it called the N-1 criterion. Basically, the network has to be designed to absorb the sudden, completely unexpected outage of any single generator, transmission circuit, or transformer. On a super dense island grid like Singapore's, a single unplanned failure just cannot be allowed to cascade into a blackout. No way!
Now, we need to be really precise about what N-1 actually means. And honestly, just as importantly, what it doesn't mean. Does it require the grid to survive losing a generator, and a transformer, and a transmission line all at the exact same time? No. N-1 is about surviving one isolated failure at a time. Multiple, simultaneous catastrophic failures? That's what we call an N2 event, which is a completely separate risk category. And 1 is just there to protect against the everyday, inevitable single contingencies.
So, to actually prove a network design meets this N1 standard, engineers use a strict checklist with 3 mandatory success conditions. First up, zero cascading failure. Basically, one trip line cannot overload the next line and cause a massive domino effect. Second, zero system instability. The voltage and frequency have to remain tightly controlled. And third, zero load shedding. That means absolutely no consumers can have their power intentionally cut just to balance the system. If a design fails even one of these, it fails the entire N1 standard.
All of this illustrates a really core reality of Singapore's power system. Redundancy is an insurance policy you never actually see. Singapore deliberately builds and pays for transmission capacity it hopes to never fully use. Think of it like a massive 4-lane highway built to handle maximum rush hour traffic, but designed so everything still flows smoothly even if one lane gets abruptly closed for emergency repairs. You don't even notice that extra, supposedly wasted capacity until the exact moment you desperately need it to prevent a total gridlock.
And we can actually see this N-1 philosophy translated into physical blueprints right at the switchgear level. Take a look at these mesh and ring busbar arrangements. During normal operation, all these breakers are closed, right? But if a fault happens, or if they need to do maintenance, the looped design means power sources alternate with loads, so a single tripped breaker never actually isolates the power.
Let's look a bit closer at how they achieve this at the absolute highest voltages. This is the 1.5 circuit breaker system, and it's deployed in the huge 400 kilovolt and 230 kilovolt generator switch houses. Instead of the standard 1 breaker per circuit, this system uses 3 breakers for every 2 circuits. It's kind of like having 3 exits for every 2 rooms. You can completely close off one exit for repairs and still safely get everybody out through the other 2. It essentially buys near-zero downtime exactly where reliability matters the absolute most.
Okay, so before this, you might have only known about the basic voltage tiers. But now you know the N1 criterion and the incredibly complex above-ground switchgear that makes it all possible. Next up, though, to see one of the most extreme physical expressions of this redundancy, we actually have to look down. 60 meters. Let that sink in. That is the jaw-dropping depth of Singapore's cross-island underground transmission cable tunnel system. To put that into perspective, that's equivalent to a 20-story building buried straight down into the earth, and it spans 40 kilometers across the entire island. It is absolutely massive. Burying these vital transmission cables this deep acts as the ultimate physical insurance policy.
Up on the surface, land is super scarce and highly vulnerable to things like construction accidents, MRT expansion, and just heavy utility congestion in general. So these tunnels were built with a massive 120-year design lifespan to safely house the 400 kV, 230 kV, and 66 kV high-voltage cables. It completely removes the very backbone of the grid from right-of-way disputes and surface-level accidents. It is literally redundancy protected by millions of tons of solid earth.
But engineering never stands still, and the grid is currently facing a massive shift. So how does this incredibly strict N1 redundancy standard hold up as Singapore undergoes the green energy transition? The grid is becoming vastly more complex for sure. We're integrating intermittent domestic solar power, we're planning huge subsea imports of clean power, and we're facing absolutely massive load increases from things like electric vehicles and energy-intensive data centers.
And this actually brings us to a really fascinating paradox from Puakak Keong, the chief executive of the Energy Market Authority. He points out that as we use more diverse energy sources, distribution lines and substations may become locally congested, which creates pockets of undersupply. So here's the paradox. You can have enough overall power generation to easily satisfy the N1 criterion on a macro scale, but local, hyper-specific imbalances can still impact energy reliability. Think about it. How do you plan for one failure when volatile power is suddenly coming from everywhere, all at once? Solving that localized paradox, that is absolutely the next great engineering challenge for Singapore's grid.